My project is titled Facial Recognition Door Lock using histogram-oriented gradients and support vector machine. I developed the idea for this project while I was trying to enter my home and found it inconvenient to look for my key. Traditional key lock mechanisms are outdated and haven't kept pace with modern technology. While smart door locks are a solution and have gained popularity, further innovation towards a smart door lock using facial recognition technology has yet to take hold in the market due to concerns about accuracy. With such a swift growing popularity, many are beginning to question the accuracy of the technology. The purpose of this project is to test whether a smart door lock can consistently and accurately use facial recognition to identify a person's face. After conducting background research, I've learned that facial recognition technology has actually existed for almost 60 years. However, it is only beginning to be implemented. Retailers such as Apple, Macy's, and Albertsons are beginning to use facial recognition technology. Similar technologies are being used in fields such as law enforcement, forensic investigations, and airlines have already begun to implement the technology. I've hypothesized that if a program is created that encodes a reference image into a histogram of oriented gradients and then compares it to real-time video using the support vector machine with a tolerance of 0.3, the algorithm will be able to consistently identify a user's face and differentiate them from images of their face within a variety of lighting conditions. The procedure for this project began with connecting the circuitry. Next, the Raspberry Pi was connected to the keyboard, mouse, and power. Then, the necessary libraries were installed, the reference images were taken, and 3 scripts were written. The observations were separated into 3 stages. The first stage tested whether the algorithm could differentiate the subject's faces from similar faces. I'd like to note that each setting combination was tested 15 times across 3 subjects. The second stage tested whether the algorithm could differentiate the subjects from images of their faces. And the third stage tested whether the algorithm could perform accurately within a variety of lighting conditions. Let's view the observations. When using a tolerance of 0.6, the algorithm was able to recognize the subject's faces consistently, but not differentiate them from similar faces. The average face distance was 0.43. The tolerance was then lowered to 0.3, where the algorithm consistently recognized the subject's faces and differentiated them from similar faces. In the second stage, the algorithm was not able to differentiate the subject's faces from images of their faces when using the previous settings from stage 1. The tolerance was then lowered from 0.3 to 0.29, where it performed flawlessly. In the third stage of testing, the algorithm performed perfectly unless the reference was taken in LED lighting, which could be considered dim or even dark. Now, let's analyze the results. Stage 1 began with a tolerance of 0.6, where it completely lacked the ability to differentiate the subject's faces from similar faces. The average face distance of 0.43 signified that 0.6 was too high. This tolerance was then lowered to 0.3, where the algorithm performed successfully. I had noticed that when using a tolerance of 0.3, the average face distances were decreased by almost half, resulting in an average distance of 0.26. The reason for this is that the default tolerance was 0.6, which was too high, as shown by the 0.43 average face distances. In the second stage of testing, the previous settings were used. The algorithm performed mainly successfully with few failures. The tolerance was then lowered to 0.29, which worked flawlessly. In the third stage of testing, the results suggested that the algorithm could not use real-time video from all 3 lighting conditions if the reference was taken in and only in LED lighting. To continue to improve this project, the recognition and encoding speed can be improved. The algorithm took roughly 10 seconds to complete this process each time. This would require faster hardware. The accuracy of the data could be improved by using more subjects. In order to create a potentially conclusive answer, these tests would need to be expanded to hundreds or possibly thousands of subjects. This is the door demonstration that I have created to demonstrate the use of facial recognition technology in the form of a door lock. This was the circuitry used to create this project. Here you can see the 12-volt solenoid lock. Over here, we can see the Pi camera. Over here, we can see the 5-volt relay. And over here, we can see the power connections. Notice that the solenoid remains locked while unpowered. The hole was created to allow the camera to record real-time video of the user's face. Notice that the door is locked. Here, I will be using an image of myself on the door. You'll notice that the image does not work. Now, when I hold my face up to the door will unlock. And the door can be opened. After carefully analyzing the results, here's my conclusion. The hypothesis states that when using a tolerance of 0.3, the algorithm will be able to consistently identify the user's face and differentiate them from images of their face. This hypothesis was mostly supported, as when using a tolerance of 0.3, the algorithm was not consistently able to differentiate the user's face from images of their face. Although this hypothesis was incorrect, it was close, as when using a tolerance of 0.29, the algorithm was able to identify the user's face and differentiate them from the images of their face flawlessly. These tests support the hypothesis and have proven that facial recognition technology is indeed accurate enough to provide sufficient security. This work has the potential to be applied in the home entry and security industry. This work suggests that facial recognition technology can be used as a sufficient method of home security. This work has great importance because facial recognition technology is rapidly gaining popularity, and as a result of this, it has sparked a large controversy. The purpose of this project is to test whether facial recognition technology can be used as a sufficient method of home security and can provide users with assurance of their safety. The main difficulty that I had faced throughout this project was debugging the software. It took weeks to overcome all of the issues I had faced. I had overcome these issues by creating my own solution from similar solutions I had found online. What I enjoyed most about this project was the feeling of relief when I had finally overcame all of the issues. I would like to thank my science teacher, Ms. Longden, for her support during this project. For more details regarding histogram of oriented gradients and support vector machine, as well as samples of code used in this project, please refer to the written report. I hope this project has helped you to gain a better understanding of facial recognition technology. Thank you.